Hello everyone. Uh, how are you? It's very good weather today outside, but we have to study now. So from now on, today I want to explain what is a functional dependency. Functional dependency. Okay, so it is very basic uh, in our relational models. Okay, so before we start, I want to wrap up. What is function? Do you remember high school mathematics? So I'm sure that you already have learned the definition of function. Function. Okay, so the function itself is a kind of a mapping. Mapping. So mapping means that there are two sets, X set and the Y set here. So among the elements in each set, they can be mapped between these two sets. That is mapping. Mapping. Okay. So if there is one mapping from X to Y, we can call X set is domain. Domain. In Korean, it is a 정의역, and Y set is called codomain. Okay, it is a 공변역 in Korean, and especially the subset of Y that are mapped from the X set is called Y prime, is called range. So we are very interested in the domain and the ranges in mappings. So we can define mapping between two sets, X set, domain set, and Y set, range set. Okay. Among this, the mapping is a more general concept than functions. So we can think many types of mappings. Among them, the simplest one is one-to-one mapping. Means that each element in both set, x1 element A, B, C, y1 set has 1, 2, 3 element. Then there are one-to-one mapping between the elements in each set. So A will map to 1, B will map to 2, C will map to 3. Okay, each element will be mapped to only one element in range set. In that case, it is called one-to-one mapping. Okay, and there are one-to-many mapping also, means that only one element will go to another set element, but y2 set element may have many values. Okay, this example shows that one-to-many. One element in y2 set has two mappings. Okay, but every element in x2 has only one mappings. So we can call one to many mappings. Okay, and third type is that the reverse of 1 to m. M to 1 mapping means that domain set element has two mappings. Two mappings. Okay, so here A has two mappings to 1 and 2 element in Y3. In that case, it is called many to one mappings. Okay. The other one Last one is that no mapping. Yes, there is no mapping element in domain set. In this case, Y2 has no mapping element 3. Y2 is range. Range codomain. Codomain may have no mappings, but domain cannot have no mapping element. Okay, so among these 4 types of mappings, only 2, F1 and F2 is called function. This 1-to-1 mapping is also function, and 1-to-M mapping is also function. But we do not call function. We do not call M2-1 mapping as functions. This is no function. And no mapping also is called no functions. Okay, so here only 1-to-1 and 1-to-M mappings belong to function. We can call function 1-to-1 mapping or 1-to-M mappings. Okay, what is the meaning of the function? So the X set, domain set, is called determinant. If X set is determined, is fixed, then the Y value will be determined. Okay, in that sense, X1 is called determinant of these mappings. Okay, and Y1 is called dependent. Okay, so here determinant and dependent exist in each mappings. But if you see M2-1 mapping A1 is not determined, even though you know A, but you do not know what is mapped to the A, 1 or 2, we don't know. So it is not determinant. So that means that it is not function. Every function, domain element must be determinant. Okay, so no mapping case, C element is not determinant because there is no mappings. In that sense, no mapping case is not functions. Only 1-to-N and 1-to-1 and 1-to-M mappings are called functions. Okay, okay, that is about functions. Now we can say that this X and Y values are columns of the tables, or columns, attribute. Between attribute in relation, we can decide if it is a function or not. If it is 1-to-1 mapping or 1-to-M mapping, it is a function. But it is a M2-1 or no mapping, it is not functions. Okay, so that's the basic concept of this function of these chapters. So let's go on next. Okay, now we can define functional dependency between attribute or columns. So functional dependency occurs when the value of one attribute determines the other value of a second attribute. Then we can say that if it is determined, means that it is a function. Okay, so we can say that the relationship between two attributes satisfy this one. We can say that it is they are functional dependency. So the first attribute is called determinant, and the second attributes are dependent. So this means that student ID columns, student ID attribute will determine student names. Okay, what is the meaning of that? So if you know what is a student ID, then you also knows what is a student's name. Okay, because it is a 1-to-1 mapping or 1-to-many mappings. Okay, so do you think that the reverse is okay? The reverse is also functional dependence. That means that student name will determine student ID. Is it true or not? This is a function. But can you decide that the reverse is a function or not? No. Why? What is the counter example of that this is not functions? Can you guess what? So if two students has the same names, then it's a homonym, homo named. Then it is many to one mappings. Then it is not functions. So even though we know the name of the student, we do not know what is the student ID. Okay, so the reverse is not functions. But student, if you know student ID, then you surely knows the name of the student. Okay, so that is functions. How about this one? Student ID will determine dorm name, dormitory names, and the dormitory room and the fee. Is it true? You must decide one by one. Like student ID will determine dormitory name. So if you know student ID, then you surely knows where this student live in the dormitory. Okay, so it is functions. How about dormitory room? Student, if you know student ID or student number, then you must know where he or she lives in the dormitory room. Also the same way, if you know student ID, then how much is the fee of the dormitory? Okay, do you think the reverse is a function or not? So dormitory name will determine student ID. Can you answer it? So if one dormitory has many students can reside in one dormitory, then there are many students, so many to one mappings. So it is not functions. Okay, and if you extract or identify this kind of a functional dependence, then we can say that left side of the functional dependence is called determinant. Okay, so you must decide if it is a function or not based on the logics. So you can decide based on data, but data may be confusing. So you must decide if it is a function or not based on logics, reasonings. Okay, so you must decide every mappings between attribute. In some cases, functional dependency may be based on equations. In some cases, so extended price can be calculated by quantity times unit price. In that case, If you know quantity and the unit price, then extended price will be determined by using these expressions, formulas. Okay, then we can say that composite attribute quantity, comma, unit price will determine extended price. It's also true. But this is a very rare cases. Functional dependency are not always equations. It must be decided by, judged by logics. Okay, so the first step of the normalization is identifying every functional dependencies. So you must be able to decide if this is a function or not for every pair of attribute. Okay, so for example, okay, so for example, if we have one relation, object color, weight, shape, then can you identify or extract every functional dependence in this relation? So you must decide or judge every combination of attribute. If the first combination is object color will determine weight or not. So this one. Okay, so object color is red, blue, yellow. Every data are distinct. Okay, that's good to be determinant. And red will go to 5. Blue will go to 5. Yellow will go to 7. Yes, this left attribute is domain. And the right attribute is codomain. Okay, so 5 are the same one, so you may erase, delete it. So what is this mapping types? This is one to many mapping types. So can you say that this mapping is a function or not? Of course, this is a function. Okay. How about object color will determine shape or not? So the same way, object color will ball, cube. Yes, this one, and this one, and this one. Yes, it's also 1 to m mappings, so we can say that this one. Okay, how about weight will determine object color? This mapping, yes, 5 to 5 will map to red and blue. So that means that this is m to 1 mappings. So it is not functions. How about weight to shape? Weight to shape is also the same way. It is not functions. How about the shape? Shape will determine object color. This cube will have mapping, 2 mappings, blue and yellow. So it is no functions. Shape will determine weight or not. Bool will determine this one. And cube will determine this one. And the cube will determine, this one. Okay. So this way, this is m to 1. This is not functions. So we can say that only 2 functional dependence can be identified from these relations. Okay, these two functional dependence can be represented as shortly using this parenthesis. Okay, So this parenthesis means that object color will determine weight and object color will determine shape. So you can represent these two lines or this one lines. The same meanings. This is the same meanings. Okay, in this way, you must identify every possible functional dependence between attribute in relation. So that is the first step of normalizations or primary keys. Okay, yes, it's very important here. And next terminology is composite determinant. Composite determinant means that more than one attribute may be determinant. Okay, this example shows that student name, comma, class name will determine grade. So if you know student name and class name, then you can get to know what is a grade. So this is a determinant. Okay, and this is a functions. So composite determinant is possible in functional dependence. Okay, and let's go on. So if we summarize, if A will determine B and C, that means that A will determine B and A will determine C. So right side parenthesis means two dependencies, and but this left side parenthesis means that composite determinant. So both A and B will determine C. That means that A cannot determine C, B only cannot determine C. Okay, so only composite determinant A, B will determine C. Only when we know A value and B value, then we can determine C values. That is the meaning of composite determinant. So we can see that the parenthesis location is very important. So right parenthesis and the left parenthesis means different. Okay, this is an example. So we are very familiar with these tables, SKU data tables, which has SKU description, department, and the buyer attribute, 4 attribute. So among this, from this SKU data tables, can you extract how many functional dependencies? Okay, how can you start? So you can start from first attribute. SKU will determine SKU description. Is it function or not? You must decide it. So if you see this one 100 100, there is no duplicate 100 100, and every data in SKU are distinct, no duplicate. Okay, yes, no duplicate. And also SKU description has no duplicate, but department has duplicated data: water sports, camping, climbing. And the buyer, Peter Hansen, Nancy Meyer, Schindler, duplicate data. In that case, can you decide SKU will determine SKU description or not? What is mapping types? 1-to-1, 1-to-M, M-to-1, and no mappings. Can you decide? Yes, it's 1-to-1 mappings. So it is called functional dependency. Okay, so S can be determinant of SD, SKU descriptions. How about S will determine department? Department? Yes, you must examine all the data in here first. So here, this data will be, this is a one to many mappings. Okay, it is functional dependency. Yes, that's true. The same way, S will determine bias. Is it true? Yes, it's true also. But how about the reverse? SKU description will determine S SKU. Yes, it's if it is a one-to-one mappings, then it is also functional dependency. How about department will determine SKU or not? These directions. Is it function or not? No. Because M2-1 mapping is not functions. How about this one? Buyer will determine SKU? No. Okay? So in this way, we must search every functional dependency in this relation. Okay? So SKU description will determine every other columns also, and SKU will determine every other column. Every other column means that SKU will determine SKU description, department, and the buyer. SKU description also will determine SKU every other columns, department and buyer also. How about department? Department will determine buyer or other one? Department. Department cannot determine SKU, but how about this one? Department, how about, what is this relationship? Department and the buyer. Water sports is the same one, so this one, Nancy Meyer. Okay, this one, this mapping is M2-1 mappings. Okay, this is no functions. How about this one? Buyer, department. Buyer department, you can see that it is one-to-many. It is functions. Yes, it's very important here. Important here. So we can see the result of the functional dependence in SKU data. Okay, so SKU will determine every other columns, SKU description, department, and the buyer at the same time, and SKU description will determine also every other columns here, and especially buyer will determine department also. Yes, it's a very important identification here. Okay, so buyer will determines department here. Okay, so there are 1, 2, 3, 4, 5, 6, and 7 functional dependence exist in SKU data tables. Okay, that's very important here. How about this one? Second example is, yes, it's also Cape Cod database order items. Order items. So there are 1, 2, 3, 4, 5 columns here. Also, we must decide what kind of functional dependence in these tables. Okay, so we must determine order number will determine SKU. Is it functional dependency or not? No. Order number is the same, 1000, but SKU has 2 data. So that means that this is a many This is a 1. So that means that M2 1 mapping. So it is no functions. Okay? Yes. How about SKU? Will determine order number? Oh yes, it's a 1 to M mappings, so this is a functional dependency. And how about SKU will determine quantity? Quantity? No, 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 no. It's the same SKU values here, but they have a different quantity, 4 and 2. Okay, so that means that M2 mappings. So it is not functions. And how about this is not functions. How about SKU and price? Also not functions. SKU and extended price, no functions. So order number is not determinant for SKU here. And how about order number with quantity? No, 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 no. It's made different. And order number will determine price? No. Order number will determine extended price? No. So there is no single attribute that determines every other column. Okay. Then we can extend the number of columns for determinant. Okay, so if you combine 2 columns, order number and SKU, will determine every other columns or not. So this composite determinant will determine quantity. Oh yes, yes. And also price, yes, and the extended price also. Okay, in this way you can decide 3, you can identify 3 functional dependencies. And also we already have seen that equation quantity times price becomes extended price, also becomes one functional dependencies. So we can say that this one, order number, comma, SKU, combination of attribute, composite attribute will determine every other columns. And also another composite attribute, quantity and times will determine extended price. Okay, so there are 1, 2, 3, 4 functional dependencies in all the item tables here. How about? Okay, so we have seen 2 examples here, and you can try every tables you can meet. And what makes a determinant value unique? Yes, so determinant is unique in a relation if and only if it determines every other columns in the relation. So that means that the determinant is unique. Okay, so but you must be careful that you cannot find the determinant of all functional dependencies simply by looking the unique value in one columns, because the data can be very limited. Limited data can be seen in your data, and so we must, of course, so we therefore we must decide determinant logically. Okay, so every functional dependency must be decided by logical decisions. Okay, that's very important one here.